Okay, we're still in chapter 2, section 1 on functions, and now we're going to look at another goal. That will be to give and apply the definition of a function, and we'll briefly talk about using function notation. So why don't we take a look at this. The very last thing we did was plotting points and using point-by-point plotting on a grid in order to graph an equation. Well, this graph that we just created, that's actually the graph of a function. And what is the idea of a function? It's very simple. It's a correspondence between two sets, D and R, such that we say to each element of the first set D, there corresponds one and only one element of the second set R. So we have two sets, and I'm going to use these weird shapes here to illustrate sets, D and R. And we have elements, a bunch of numbers or points in one set, D, called the domain. This is called the domain, D. And the other elements here are called elements in R, the range. Okay? So all that a function does is it's a ruling, it's a correspondence, it's a rule, it's a relationship that takes elements from one set to the other. You can think of it in terms of inputs and outputs. You take an input in set D, and under some function f, let's call it, it takes that input into an output in the other set R. Okay, so we'll get back to this picture in just a second, but for now, here's an example. The cost of a pizza, which we'll denote by the letter C, is related to the size of the pizza. Everyone's ordered pizza, you guys know that. So a 10-inch diameter pizza, for example, costs $9, while a 16-inch diameter, a much bigger pizza, costs $12. Okay, well, to visualize this again with this idea of sets with domain and range, visualize a function by the following diagram, which shows the correspondence between the two sets. The domain of the function, right? This gives the diameter of the pizzas. You see, these are my inputs. These are the elements of the domain. The different diameters, 10, 12, 16. Okay? And in the range, the elements are the cost of the pizza, right? So the elements of the range here are actually the different cost for the pizza. So I have $9, $10, and $12. Okay, so what the function does is for each size diameter pizza here in the domain, it maps it exactly to one element in the range. In other words, it maps it to exactly one cost in the range, how much each pizza costs. So that's the idea. It's this sort of mapping or a relationship, again, we should say. Visually, we call it a mapping because it maps elements from one set to another. But it's a relationship that connects the inputs to the outputs, right? That's one way to think about it. Okay, so usually functions are specified by equations, more frequently in our class especially. So if in an equation in two variables, we get exactly one output only, right? So one element of the range for each input. So we get one output for each input here. Then the equation specifies a function. The graph of such a function is just the graph of the specifying equation. So this little part here is quite important. If in an equation in two variables, you need to get exactly one output for each input. Remember that, one output for each input. Okay. All right. In other words, one element of the range needs to correspond to every other, for each element in the domain, I should say, there needs to be one element in the range that corresponds to it. So if you get more than one output for a given input, the equation does not specify a function. So think of the pizza example. If you have a pizza whose diameter is 12 inches, it cannot be the case that that pizza costs $10 and at the same time it costs $15. That can't be the case. That doesn't make sense. When you order a pizza and you know that the diameter is 12 inches, it costs a certain amount and that's it. It can't be one or the other, right? So that's sort of the idea of having a unique output associated for your input. Okay, so why don't we take a look at another way to visualize these equations. So consider the equation that we have dealt with before, x squared minus 2. So here's x squared minus 2. Here's our function. It has taken the shape of a little machine here. This is our function. And here's how this machine works. you take the input of -2 and you feed it into the machine. That's where the input goes. Okay? Then what you do is, just like we did earlier, you evaluate this by plugging in -2 for x, and you get -2 squared minus 2, which is 4 minus 2, right? And the machine spits out the answer, which is 2. So input, that's your -2. The process is to follow the function's rule, that is to square the input and then subtract 2 from the result, and that gives you the output, the final result, which is 2. So -2 comma 2 is an ordered pair here of this function, right? We write the input first, output second, as we discussed earlier. Okay, so that's another way to visualize a function, is to think of this machine that has an input and spits out an output. Another way to do it. Of course, a lot of the graphs are going to be presented in our class. So if we have the graph of an equation, there is an easy way to determine if that graph represents the graph of a function, and that's something called the vertical line test. It's something you probably remember from your previous math course. What does it say? It says an equation specifies a function if each vertical line in the coordinate system passes through at most one point on the graph of the equation. So each and every vertical line in the coordinate system passes through at most one point on the graph of the equation. If any vertical line happens to pass through 2 or more points on the graph of the equation, then the equation does not specify a function. And here are some examples of this. If you look at this first example, we have a graph of some equation here. However, this graph is not the graph of a function, because you can draw a vertical line, namely this red line here, which crosses it twice. It crosses my graph at 2 different places. I can draw another vertical line here that does the same exact thing. So the vertical line test says this is not the graph of a function. Not the graph of a function. On the other hand, here's a nice, it looks like a trigonometric function that's been graphed. Notice this is the graph of a function, because any vertical line that you could think of, any vertical line, will only cross my graph once. So here is another one, here is another one. I can come up with any vertical line that I want. It's only going to cross once.